In this next section, we're going to be talking about concepts called work and energy. We'll talk about this diagram in just a second. We all have an idea of what we mean by work and energy. We all, I don't know, you probably said, like I have, I don't have the energy to do this today. I don't want to do that work. I don't want to go to work. So energy is kind of hard to define, like with a specific definition. But energy is some sort of quantity an object or system has that can potentially make it move or related to its motion, that sort of thing. So when we look at this diagram here on the left, a system is going to be any type of object or system of objects, combination of objects that are moving or can move or will move or were moving. Some sort of system that we're going to analyze the motion of. So work and energy, we're going to be analyzing motion. The last section, we were analyzing motion as well, where we were talking about the net force acting on an object or system of objects and causing those objects to accelerate. Work and energy is another way of looking at motion. It is a little bit different. It does relate forces to speeds and distances and heights. So kind of skipping out the acceleration step. So our system is going to be the object or combination of objects that we are going to be looking at. We talk about the system having a total amount of energy. Capital E for the energy, and then SYS as the subscript to represent the system's energy. There are different types of energy. We are going to start specifically talking about kinetic energy. Kinetic energy is the energy an object has due to its motion. So an object, a set of objects are moving. When they're moving, we say they have kinetic energy. So that prefix, kine, we saw with kinematic equations. Those were the equations of motion. So kinetic, we're talking about the energy an object has because it is moving. On our generic or general equation for kinetic energy, we're going to use a capital K to represent kinetic energy. The amount of kinetic energy an object has is directly related to its mass and how fast it is traveling. Kinetic energy is a scalar, not a vector, meaning the object has kinetic energy or not, or it doesn't. So it's either moving or it is not. Kinetic energy is positive because V is squared. The direction actually doesn't matter. So if an object is moving, it has kinetic energy, and we will use 1/2 mv squared to represent that. Potential energy has to do with interactions between the system and like the force of gravity. So we're going to be talking about potential energy due to gravity. We consider potential energy as stored energy. So somehow there's this ability, because gravity, the earth is there, gravity is going to act on this object. There's this ability for the object to move because of gravity. Potential energy is specifically addressed in chapter 10 though. So in chapter 9, we won't specifically do anything with potential energy yet. Chemical energy A common example, food. Food you eat. You eat breakfast, you eat lunch. We have to have some food in order for our bodies to work. Another type of chemical is gasoline. We have to put gasoline in our cars or our lawnmowers or our motorcycles. That chemical storage, that chemical reactions have the ability to make the car go when it is used properly. Thermal energy we will look at specifically with kinetic friction. Right now, if you rub your hands together, for example, your hands get warmer. Thermal energy is always related to a change in temperature. Right now, we're looking at specifically kinetic friction, making that happen. And so that interaction as an object slides on a surface of some sort. Within a system, the energy can easily or can be transformed from one form to another. That's why all these little arrows are in here. We can convert and change energy back and forth. If the system is isolated, we say that the energy of the system is constant. We say it's conserved. Energy of the system. Chapter 10, when we introduce potential energy and thermal energy and kinetic energy all together, we're going to look at what we mean by conservation of energy. Now, this diagram, though, is not representing an isolated system. So what we're seeing is there's an environment, some sort of surroundings, something outside of the system. And from that environment, work and heat are two ways of transferring energy into the system or out of the system. If somehow energy is transferred in to the system, we're going to say that work or heat is positive. If energy is transferred out, we're going to say it's negative, meaning it has been taken away from the system. So positive work or heat is putting energy into the system. Negative work or heat is taking energy out. So these big purple arrows at the top are representing somehow energy added, so plus. The arrows at the bottom are representing energy removed or taken away. So heat is something we're going to talk about when we get to chapter 19. Heat and work are both ways of transferring energy either into or out of a system. Work is the one we're specifically going to talk about now. The physics definition of work is that it is a transfer of energy either in or out of a system by forces that cause motion. That's really not the best way to put it, but forces that, here, let's do this, that act while the object moves. And by object, this could also be system. So while this object or system is moving. Work's a little more specific than that, which we'll get to. I'll start the next video talking about work specifically. Heat is a transfer of energy. Because the system and the environment have different temperatures. So you have your cup of coffee, it's too hot to drink, you let it sit for a while and come back to drink it. It has cooled off a little bit. That is an example of heat. Some of the energy transfers out of the system, which is the coffee, the cup of coffee, and it goes into the environment, meaning the air within the room. But again, right now we're focusing on work. We will talk about heat in a later chapter. So next video will be about how we calculate work, what we mean by work, and we'll continue with that.